So let's start that um, uh, about what happens to the energy in the sport. Okay, so for example, in the case of in the case of um, in the case of this interference, we got band like this. We get like this is the position of bright. Okay, we get the alternate band, so we get the dark position. Again, we get bright. So this kind of alternate bright and dark keep going in the case of this interference light interference. So we want to show here is that in those regions in the region dark, the energy lost, the energy of the region of dark spot or dark fringe actually shifted to the region of bright. Region of bright means energy is not lost. So it still follows the principle of conservation of energy. Okay, so we want to prove that. So let's start with if you remember, we have two sources, S1 and S2. It also produces the wave, trough and crest, and this also gives you the waves. Okay, they may have constant phase difference, say phi. Okay, so we know that if S1 and S2, these two are coherent sources, then we know that they have nearly same frequency. Okay, they are same frequency, means same color and same amplitude. Okay, we are taking same amplitude. So if you remember, amplitude means this is equilibrium, this is the amplitude, okay. So amplitude means displacement, but it should be highest one. So let's say let's consider the fields from S1 and S2. Okay, so say this is E1, means you know that electromagnetic wave is a combination of electric field and the magnetic field. Here we just consider one field, so we are taking the electric field. Okay, so E1 is E naught sine omega t. Okay, so E naught is the amplitude. So for example, this is E naught. This will be E naught. Okay, E1 is the value at any time t. Similarly, we can represent E2. So it has E naught sine omega t plus phi. So phase difference between these two waves, we consider it with pi. So pi could be anything. So pi could be anything. Could be like, it could be pi, 2 pi, or it could be even pi over 2. It could be any value. Okay, so in general, we call it angle phi. So our goal is to find, if we have S1 and S2, if we consider the point P here, we want to find the resultant value at point P. Okay, so we say resultant, so just to give some name. So resultant value we consider is E. Okay, so let's find the E. So resultant field. Okay, so the resultant field, at any point say our point is P, okay, is given by is called the superposition principle. Superposition principle. Okay, so what you mean by superposition principle is that net intensity will be the sum of these two. So E naught sine omega t plus E naught sine omega t plus phi value. Okay, so I can take out E naught, then I just doing some trig sine omega t plus phi. Okay, next I can write further simplification. I can do as 2 sine, this is just like C plus D formula. Okay, sine C plus sine D, it will be 2 sine omega t plus phi over 2 times cosine omega t minus omega t plus phi over 2. Okay, then if I simplify, I can write it as 2 epsilon naught, so sorry, 2 E naught times sine, this will be omega 2 plus phi over 2, and I can write this as further simplification gives me cosine phi over 2. So you know that phi is constant. Okay, phi has constant value. So if this is the case, we can write this as 2 is constant, E naught is constant, cosine phi over 2 is constant. So this sine omega t pi over 2. So this means this is the amplitude of resultant wave. Amplitude of resultant wave at point P. Okay, so this is the amplitude. If you remember the amplitude kind of thing, if we have one wave, this one first wave, if we have second wave, first wave has in amplitude E naught, second wave has amplitude E naught. If this is in phase, the amplitude will increase. So this is the resultant wave. So this is telling you that this is the first wave, this is the second wave, this is the resultant wave. Okay, so this amplitude now is given by this. Okay, 2 E naught times cosine omega 2. Okay, so let's simplify further. So we know that intensity from the wave, intensity at a point is actually proportional to the square of the amplitude. The square of the amplitude. Okay, the square of the amplitude. So this means we say I naught, but be careful that I naught here is the resultant, not for one individual, resultant intensity. This will be the square of amplitude. Our amplitude is 2. Our amplitude is 2 E naught cosine phi over 2 squared. Okay, so this means the resultant intensity I naught will be 4 epsilon naught E squared cosine square phi over 2. This is one of the result. Based on that, we can say we can define some of the terms. So for example, at say For example, if the point P is bright, position, if point P is the bright, then our phi angle could be 0, could be 2 pi, could be 4 pi, okay? Or in terms of the part difference, which is equivalent to 0, lambda, 2 lambda kind of thing. So you see, in this case, I naught, if you plug any value, 0, 2 pi, it comes to be 4 epsilon naught squared. So it's telling you that the resultant intensity has amplitude 4 times. So this is the resultant intensity is 4 times. 4 times the intensity of each individual wave. Okay. Say, let's talk about the other spot. It's called the, not the bright, we can talk about the dark spot. Let's see what will happen. At that scenario, say, if the point P is dark, if the point P is dark fringe, in that time, the value of phi will be pi, 3 pi, 5 pi, or in term of part difference, okay, in terms of part difference, we can write it as, in terms of part difference, it will be lambda over 2, 3 lambda over 2 kind of thing. It will go like this. Okay, if this is the case, we find that the net intensity I naught, will be 0. You can plug the values of P over the equations. So this means the superposition follows the principle of conservation of energy. So this means the superposition of waves in interference follows the principle of conservation of energy. Okay, so energy of the position which is dark, it actually moved to the position of bright. Okay, so this means if we plot, let's plot how it looks like. Okay, say let's plot here. Okay, so say this is our bright, then we have first bright, then second bright. Similarly, say this is the central bright. Okay, this one corresponds to first bright. It happens to the both sides of the screen, so it is like this. Okay, just like that. So this will be the, again, first bright. This will be the position of second bright. Okay, similarly This is the second bright. So you see the intensity this of each is 4 times of intensity of each wave. Okay. If you consider the each wave, individual wave, intensity is E naught square. So for each wave, each individual wave, say this is the wave first, this may have wave second, then this amplitude will be E squared. Okay, so we just, this is also E naught squared. We're talking about intensity. So you know that for the central bright, if you consider in terms of angle or in terms of phase, we have the relation as we talked before. Okay, so we are talking here. So for example, we have these two sources. For example, we have source S1 here, we have S2 here, then this is the central bright, this is the first, second bright kind of thing we'll get from this part. Okay. So let's move to the further. In interference in thin film, for example, the soap bubbles exhibit brilliant colors when exposed to the sunlight. So this is because of interference in the thin films. Okay. So for example, the incident light, this get reflected from first surface here. So this one is the reflected one from the first surface, and this one is the reflected one from this bottom surface. Okay, so these two reflected waves interfere. So interference happens between these two reflected waves. That's how we see the different color. If we have only one color, then we just get bright and dark. But okay, but if we are using not the single particular color, then we also get this kind of not only one color, this kind of colored image. Okay, so let's see one simulation I may have here. Okay, so in thin films, so we can change how the thin film go, how they interfere. Okay, so we can play around with this kind of thing and see how the refractive index also changes that. Okay, so this is about the interference in thin film, and the case is about the ring. We are talking about the Newton's ring. So what does it mean by Newton ring? Okay, let's draw one picture over here and see also one of the simulation I have here. Okay, I will play that simulation at first. Say this is the lambda color, the wavelength is particular color. Then you can see how the interference pattern ring looks like. If you change the wavelength, color would also change accordingly. Okay, so this means in the case of ring, the theory behind of this ring is this. Say we have a surface here. Say for example, this is the surface. Say for example, this is the plate. Say I take the glass plate over here. Okay, then I put lens. Okay, so you know that this is the convex lens. Okay, so you know in between the area here, this is the air. You can put the water also if you want to find the refractive index. This method is used to find the refractive index of different liquid also. Okay, but here I'm assuming the air. So we call it air film because a very small thickness of air layer happens. Say, for example, I hit the incident light here. Incident light, okay? Incident light. Say I just use, for example, say this color is, say, for example, one particular color, say I use the yellow color only. Okay, I just example. So what will happen? Again, as before, reflection happens from this surface, and this light travel from air to glass, glass to air, and reflection happens from this bottom plate. And again, after reflection and refraction, light could go like this. So if we are here, this light interferes. This light interfere, and interference phenomenon happens. Because of that, we see this kind of colored band. So for example, if you are taking particular color, the central may be dark, okay? Then we see the band, white band. Again, we see the band is white, again dark, and white, this kind of color band, color ring. So this is called, this band, this alternate white and dark band is called the Newton's ring. This happens because of this called the interference phenomenon. So as you see in the simulation, it depends which kind of color we are using. Say for example, I start with the light having color of wavelength 407 nanometers. So these are the incident wave is reflected, and we see this kind of color band. Okay. So this is all about this ring, Newton's ring. This is the very good use of the Newton's of the interference phenomenon. And this is one of the important experiments. It's called the Michelson interferometer. And this also explains how interference phenomenon we can observe using a combination of meters. Okay, so we can, this is one of the best example, and this method can be used to find the refractive index of different kind of glass, different kind of object materials. This method can be used. Okay, so in practice 2 question, I expect you explain the physics behind this Michelson interferometer. It is in the textbook also. If you use any external resources, you have to cite. Okay, and there are a lot of resources in this link. You can use that if you want, you have time. Okay,